Hello, in this video recording, we are going to learn about velocity relay algorithm for solving the Newton second law. Relay algorithm is basically a numerical method that you apply to try to figure out how a particles will evolve or move under the force according to Newton's second law. The idea is actually quite simple. You can imagine that you have n particles subjected to a force. So you can see that here F denote a force that is acting on n particles. So under the force, the particles would accelerate according to the Newton's law, which is equals to F equals to ma. Here A is actually an um, mathematical descriptions of how the particles would change its state of motion. So the particles at any instant of time is described by its so-called vector location vector R. As time passes by under the influence of the force F, then the particle's position will change from time to time. Say at time t, say t1 is located here. Under the force, then the particle will move to another location at t2, and as time evolves again at t3, then the particles will be located at the new location. So under the influence of the force, the particles will change its position from one point to another. And what we are trying to do is that given the knowledge of the force acting on the particle, how could we calculate the locations or instantaneous location of a particle at any instant of time? Then visualize the location for every snapshots of time that would then simulate the motions of the particles. So this is basically the purpose of the Rayleigh velocity algorithm. The main input that is required to simulate the motions of particle under the influence of the force is the knowledge about the force F. However, in actual situations, what is actually really required is force divided by mass, which is the acceleration. So the idea is if you know how the acceleration is acting upon the particles, then using this knowledge of the acceleration, you would be able to figure out how the particles change its position as a function of time. Let us look at a very simple example of a pendulum that is influenced under the restoration force in the case of a simple harmonic motion. So if you can recall your knowledge from the previous study in your first year basic mechanics, the force acting on the simple harmonic motions is in a form that is proportional to the displacements. X here refers to the displacement of a particle from its initial position. So you can imagine that initially you have an reference point that the particles is located at somewhere here. Then when you displace it by some small displacements, which X is referred to the displacement from the equilibrium position. This is the equilibrium position, equilibrium EM. Then the force will try to restore the mass towards its equilibrium position. So this is the characteristics of an restoration force. And under this restoration force, the object or the mass would then execute a simple harmonic motion. So in order to describe the simple harmonic motion, you write down the equations of motion for this system. So the equation of motion for this system is actually the applications of Newton's law on the particle. So let us try to explain how you would write down the equation of motion for the simple harmonic oscillator. So imagine that you have a simple harmonic oscillator which has which is a mass m, and it is being linked to a spring which has a constant k. So initially the spring is relaxed and the particles is located at its equilibrium position somewhere here. Okay, so we call this a location of x naught. Then when you pull the particles a little bit further away, then it will be extended, and we call this displacement of the particles m from its equilibrium position as x. So x here refers to the displacement in the position of the mass m from its equilibrium position. And as a result of such a displacement, restoration force will be acting on the mass. And this force is actually coming from the spring. So the spring will exert a force which is uh, opposite to the displacement. So this is the net force that acts on the particles. According to Newton's second law, the net force F will cause the particles to change in its state motion uh, by following this F equals to ma formula. So here the A refers to the second order derivative of the position with respect to time. So on the left hand side refers to the restoration force, and then the right hand side here is referring to the acceleration. So this is an second order differential equation, which is just a different forms of the Newton's law by slotting in the expression of the force from the spring acting on the particles. So you make some small rearrangement, then you would have these situations of the accelerations of the uh, object m, which is I denote it as ax, by definition is the second order derivative of x with respect to time is then equals to minus omega square x. Here omega square is just a positive constant denoted as the spring constant divided by m. Okay, so here k and m are both positive, therefore omega square is a positive number. So given a system that is fixed in the mass and is spring constant k, then omega is constant. Here omega is known to be the angular frequency of the simple harmonic system. So this is the what you call equation of motion for the spring mass system. So once you have written down the uh, equation of motion for the particles, then it is now possible to apply velocity Rayleigh algorithm that will allows you to trace out how the particles position x changes from time to time. So in the actual situation, when you set a oscillator, simple harmonic oscillator uh, into motion, you first have to specify the initial condition to the system. There are two initial conditions for a system that is described by the Newton's second law. So Newton's second law is a second order differential equation. Therefore, you need to provide two initial conditions. I write it as IC, stand for initial condition. One initial condition is the locations of the position at the time t. So I denote it as x0. And the second um, initial condition that is required is the time derivative of the position at the time t equals to 0. Here is the initial locations when you release the oscillator from rest, and this is the initial velocity when the particles or the oscillator is being released from rest. So if you draw a pictures on this, say this is the natural length, which is denoted as x naught. So to set the particles or the oscillator into motion, what you do is you displace it from some initial position, say like this. So initially, the locations, the position is displaced initially at say x equals to a. Okay, so in this case, you displace the positions of the object initially at time t equals to 0, and then your x is set to be a. So where a is just defined as the distance between the equivalent position and the final position before you release the particles. Okay, and it is possible that we release the particles by not giving the m any velocity. So you can just pull it and then just release it. So when you release it, the m initially will not have any initial velocity. Therefore, we can write this Vx at 0, which means the velocity of the particles at the beginning of the time t equals to 0, which is alternatively written as x dot 0, is also set to be 0. So this is a very simple example where you set the equations or you set the motions of the simple harmonic oscillator from the beginning t equals to 0 by releasing it from an maximum displacement of a and with an initial velocity of 0. So given the knowledge that the accelerations of the particles is equals to minus square x and x not known to be a and the x dot 0 known to be 0. With these three initial conditions, then we can then write a code to describe how the x of the particles could be calculated from one time step to another time step. So as I mentioned in the other similar simulations in the previous topic, the uh, simulations procedure based on velocity Rayleigh algorithm is done as follows. First of all, you have to figure out how large is your simulation box, and then you also have to figure out how long is your time grid. That is, how many, how long you want to simulate the time. Let us try to look at the the time grid. That is, you have to know how long you want to simulate. And if you understand the physics of the problem, it is known that for such an simulations of a simulator, the oscillator is executing a simple harmonic motions based on the strength of the K and also the mass of the M. And the frequency or angular frequency is just determined by square root of K over M. So here the period is defined to be omega. Uh, so let's say omega equals to 2 pi over t is the relationship between the period of the oscillation and the angular frequency. Therefore, the period is known once you have fixed the omega. So in this example, the k of the spring and m is assumed to be assuming some number which is known. Then you know exactly what is the frequency or angular frequency of this simulator. Therefore, knowing the omega, you would then be able to tell what is the period of the oscillation. Therefore, the length of the simulation has to be expressed as in unit of the period t. So we can try to figure out how long you want to simulate. So usually you have to simulate uh, the length of your simulation from t equals to 0 up to a multiple of the period. Say, for example, 2 period or 3 period. And then you could then specify how many grid lines you want to have between the t. So if this is a t grid, then you start from 0 and you end at t last, where t last is the length of your simulation. If you set the t last to be t2t, then it is possible for you to figure out how long it is.